Okay, so today we're going to look at modeling situations with differential equations. We won't be necessarily like setting up our differential equations and solving things with them, but we're just looking at the context. Honestly, I think this section is more of like a reading section than it is anything else. So a differential equation relates a function to that function's derivative. Okay, and we have already seen super simple differential equations. Okay, we have seen differential equations where more or less what we have seen is that instead of putting y prime or f prime of x, we have said dy over dx, right? We particularly use that notation a lot whenever we were doing our implicit differentiation, those equations where we had an x and a y. So when we took the derivative of anything with a y, we had to put the dy dx with it. So we have already seen some of this. This is differential equation notation here. And I'll go ahead and show you real quick, like that first one, how we would solve that differential equation. To solve that differential equation, we would need to get our dx over here on this side. So we'd multiply by dx. We would have dy equals, we would need some parentheses here, 3x plus 2 dx. And then we would integrate both sides there. That dy doesn't have anything with it, so it's got like a 1 there. So if we integrate 1 with respect to y, not with x, we just get y, right? Because we've got like a y to the 0 power. We've increased its exponent by 1, divide out front by the 1, so we just get a y there. And over here, we would get x squared. We'd have to divide that 3 by 2, and we do 2x, and we put a plus c over here. So that really is just asking you to integrate, right? So what we've seen this before. We've also seen second derivatives that had this notation right here. So we've seen it, but we've seen it in the most basic of contexts, right? We will be looking at situations that are a little more complicated than this in this unit, okay? So we're going to start off by talking about, just setting this up in context of the situation. So something that used to, this was in Math 1, and really it's still in Math 1, we just don't use this phrase very much. We need to talk about being directly proportional. So directly proportional, if two quantities A and B are directly proportional, then A equals K times B, where K is a constant here. So directly proportional, what you're most likely to see for directly proportional is like y equals 2x. That is a directly proportional relationship, right? So a really good example of something that would be directly proportional would be how many hours you work and how much your paycheck is for if you're an hourly employee, right? So, you know, if you're a part-time job, you get paid $12 an hour, and you work 8 hours, you can figure out what you make, right? So that would be a directly proportional relationship. So all it means is that one variable equals a constant times the other variable. It's a linear equation with a y-intercept at 0, is what we're looking at. So it tells us here the rate at which a quantity m of a certain radioactive substance decays is proportional to the amount of substance present at a given time. Which of the following is a differential equation that could describe this relationship? So this is really going to be a reading exercise more than it is a mathematical exercise. So when we see something is directly proportional to something else, right? What we're thinking here is we got A equals K times B. K right here is some sort of constant. We don't really know what number that is because they didn't give it to us, right? This is just some number right here. what we need to know is what is this variable and what is this variable, right? So when you see is proportional to, that is equal sign, some sort of constant times the other variable, right? So the first variable that we have is the rate at which M of a certain radioactive substance, right here, the rate at which this decays. So they're giving us the variable M, but it's not just M. It is the rate of M, right? So when we have the rate of M, we're not just going to have the letter M. We will have dm dt for that. And you can kind of tell from your answer choices, obviously dm dt is what needs to go there because that's there on all of those. So we got the rate that the radioactive substance decays is proportional to the amount of substance present at a given time. So B is proportional to amount of substance present. Now, they a lot of times will define these things a little better, but what do we think T is representing here? Time. And what is M representing? dm dt is our rate of whatever M is. What is M? Quantity of substance or amount of the substance. So what we have it's directly proportional to is the amount of the substance present. So you'll notice in your equations you have two different options. Some of these are t squared, some of them are m. What variable should it be? It's going to be m. This right here is your m. That's your amount of substance. So we're going to have this equals some number times m. And that means that A and C are out. Those are not the answers. Okay, but I said we don't really know what K is. How can we know which one of these is the answer? Since it's decay, we should have a negative, right? Because that rate should be negative. The amount of the substance has to be positive because you can't have negative amount of substance, right? So we should see a negative number right here. So we would pick B for this. Okay, so definitely this would be something that if you're researching radioactive substances, you would be interested in studying this, solving this out for certain scenarios and stuff. We'll get into more of that later. Right now we're just talking about how the equations are set up. All right, let's look at the next one. The population of a certain species of insect is given by differentiable function P, where P of T is the number of insects in the population. I'm going to write that down. P of T is number of insects. Okay, in millions at the time T, where T is measured in days. I'm going to put T as days. What those variables are defined as is going to be important. When the environmental conditions are right, the population increases with respect to time at a rate that is directly proportional to the population. Okay? Starting August 15th, the conditions were favorable and the population began increasing. On August 20th, 5 days later, there was an estimated 10 million insects, and the population was increasing at a rate of 2 million insects per day. Which of the following is a differential equation that models this situation? So this one's going to give us more information. We don't have to solve more stuff, but let's stop like right here and set up our basic setup for the problem. Okay? So when environmental conditions are right, the population increases with respect to time at a rate. So what is that? Population increasing with respect to time at a rate. That is dp dt. And that is directly proportional to, so equals some sort of k times, what's the other variable over here? That is directly proportional to the population. So that would be P there. We got to look at we need to look at the other information. I think it is going to knock out A and B. I'm pretty sure it's going to knock out A and B. We need to look at this other information before I can answer that for sure. Because I can't remember doing this problem last year well enough to make sure there's not a twist. All right. So, now, definitely we got two options here. I think it is probably going to be C or D. But we got 1/5 and 5. And that's not like a difference between positive and negative like it was on the last problem, right? On the last problem, we knew we needed negative because we were decaying. So we're going to have to use this information to figure out what is happening. So on August 15th, the conditions were favorable and the population began increasing. On August 20th, 5 days later, there was an estimated 10 million insects, and the population was increasing at a rate of 2 million insects per day. Which of the following is a differential equation that models the situation? Our equation does not involve T. So those dates are not something we can plug into this equation. But we do know on August 20th, there were an estimated 10 million insects. Where would that go? Where would we plug that in? That's P, right? 10 million insects goes right here for P. All right. And the population was increasing at a rate of 2 million insects per day. Where does that go, 2 million insects per day? That's the rate that P is changing, insects per day. That goes over here, too. And then so we can put our K right here. And so to solve for that K, we just need to divide by 10. And we will get 1/5 equals our K. So C is going to be our answer. Okay, questions? It's really a reading exercise mostly. This was some pretty simple equation solving, right? But I think this is a hard question because you got to get it set up right and know where to put everything. Lots of words. As far as math goes, we could give this to the 7th graders right now and they could do it. Most of them, anyway. Some of them. There. Okay. Example 3. A scientist is studying the relationship of two quantities, S and T, in an experiment. The scientist finds that under certain conditions, as the quantity of S increases, the quantity of T decreases. After taking measurements, the scientist determines that the rate of change of the quantity of S with respect to the quantity of T present is inversely proportional to the natural logarithm of the quantity of T. Which of the following is a differential equation that could describe this relationship? All right, so this one throws something new at us that I really should add into my notes right here. We've got, this one's not directly proportional, right? This one is inversely proportional. And what that's going to mean is that whenever one quantity, so like directly proportional, that's like the number of hours you work and how much you get paid, right? If the number of hours you work goes up, the number of, the amount you pay goes up. Inversely proportional is going to have the opposite relationship. So here's an inverse relationship. let's say that I were to bring in a box of cookies, and I've got 50 cookies, right? So, if I have 50 cookies, and I've only got 3 students in class, each student gets a lot of cookies, right? But what happens as the number of students in my class goes up? Number of cookies per person goes down, right? Because there's fewer cookies to go around. So, the inversely proportional relationship, let's write this up here. Inversely proportional will look like this. A equals K divided by B. Okay, so, again, this is sort of like a reading experiment here. I'm leaning towards B not being correct because that K is in the denominator there. That looks like that one's probably going to be wrong. But I'm going to have to read to figure out this other stuff right here to know. So we got S and T. S and T are quantities of some sort of substance, right? Yeah, quantity of S and quantity of T. So, after taking measurements, we determine that the rate of change of the quantity of S, what's that? That is ds dt. It is going to equal K divided by, oh wait, is this dependent upon time? I've messed this up. It's not a lowercase t. What should it be? It should be a big T, because it says with respect to the quantity of T. So rate of change of capital S in respect to rate of change of capital T. Probably you've got some sort of reaction going on here. So as the reaction takes place, like if you put baking soda and vinegar together, like over time, as those two react, the amount of one substance is going to increase, the other stuff is decreasing, right? And then we've got K divided by, let's see, inversely proportional to the natural logarithm of the quantity of T. What's that going to be? Natural log of T, right? And then so we will look to see which one matches, and I think Liam already said it. That is going to be C. You're probably right. Yep. Yeah, well, B is DSCT, but we already kind of threw that out because the K was on the bottom. Yeah. Yeah. All right. All right. 4. A jogger runs along a straight track. The jogger's position is given by the function P of T, where T is measured in minutes since the start of the run. So I like to, we got P of T is jogger's position. And T is minutes. Sometimes that becomes helpful. During the first minute of the run, the jogger's acceleration is proportional to the square root of the time since the start of the run. Which of the following is a differential equation that describes this relationship? All right, so looking at your answer choices, anybody want to? You can. Why, Liam? Correct. So we're talking about acceleration. The derivative of position is velocity. We need to take a second derivative to get acceleration. So we've got the jogger's acceleration is going to be d squared p over dt squared. That's our second derivative. Is proportional, so this is proportional. It's going to be k times something. What is it proportional to? square root of time since the start of the run. So that will be square root of t. So our correct answer for this one will be C. Okay? Questions? All right, try this next one. It is similar to one we've already seen, so try that one on your own. Okay, check with your neighbors, see what they got. See if you get the same thing. What do you guys think? I think it's C. Okay. So, weight of the yeast population increases with respect to T at a rate. What is that? dW dt, because it's weight with respect to time at, and we're dealing with the rate right here. So dW dt equals K, because we're proportional, to the what? Weight. So what can we throw out? Which answer? A and B are out. A doesn't even have anything about a rate. B is with respect to time, your proportional to time, not to weight. Okay, so that leaves us C and D. T equals 10 is irrelevant other than letting us know this is happening at the same time. Weight of the yeast is 200, so that goes here. The rate at that time is 5. If you solve for K, you divide by 200. That reduces to 1/40. So C is going to be your answer there. Okay. Questions? Yes. Everyone's here, so I doubt this will get watched ever again. But yeah. Yeah. All right. Okay. Pressure P applied to a gas is increased while the gas is held at a constant temperature. Then the volume of the gas will decrease. So you've got pressure is increasing, temperature is constant, volume is decreasing. So if you have like a balloon and temperature stays the same and you squish it, right, that pressure inside is increasing until it increases too much and then it pops. The rate of change of the volume of gas with respect to the pressure is proportional to the reciprocal of the square of the pressure. Which of the following is a differential equation that could describe this relationship? So this one, let's throw in some new stuff in here. Alright, so we know we've got directly proportional. We're going to have equals K times something there. Although, look at your answer choices. Are any of them K times something? No, but that's how we're going to set it up at first anyway. Okay. Alright, so the rate of change of the volume of the gas with respect to pressure. What is that? dV dP. So rate of change of the volume that goes on top of the gas with respect to pressure, that goes on the bottom here. So that is going to be dV dP.
So the rate goes by.
I'm not sure what that comment is. I'm unfamiliar with this, but I would like to.
Where do you hear now?
This is Allegheny County thing, I think. I don't know if we do that in Surrey County. All right. It's proportional to the reciprocal of the square of the pressure. What does that mean when I have the reciprocal? What do you mean reverse? Okay. Fraction is flipped, right? It's not the sign changing, because reverse could mean like the sign is changing, or it could mean that you're flipping the fraction. So reciprocal is flipping the fraction. So the reciprocal of the square of the pressure is going to be 1 over pressure squared. Okay? All right? So, which ones are out? A is out, D is out. Okay? So now, B and C have the same differential equation, but for one of them K is positive, and for one of them K is negative. So, we know, gosh, pressure is applied to the gas. It's going to increase. So we're talking about how the volume changes as the pressure changes. I'm going to think about this for a second. All right, temperature just is held at a constant pressure because temperature can also affect your volume. So that's not really a factor in this. Pressure is applied to the gas. The volume will decrease. So the rate at which the volume changes as the pressure increases. So as pressure increases, volume should decrease. So maybe we'll have to go look at the key for this one. I think we gotta have negative. Let me see if I have the answers to this one though. Might should have looked through this one before we began. I don't have the answers. Alright, this is from AP Classroom. Look at the next question while I confirm that in fact is negative. Well, that, oh gosh. Okay, well let's look together and make sure that Miss Hyatt knows what she's talking about. I'm not inspiring confidence in you guys right now, I'm sure. Yeah, the only thing that's got me worried is that reciprocal, because you're dividing by P, and alright, we want unit 7. This is topic questions. That's going to be this one. Wait. That's not this one. It's negative. We were correct about the negative. We were right. It's C. Because although you are dividing, that still doesn't change the sign, because that's a positive number. So, okay. All right. So,